Hi. So today we are going to do our recitation on mathematical induction. And before we even start, I suggest you go back and really watch the video on how Dr. Jacket produced this chapter. He explained a lot of details there that are going to be very useful on proving using mathematical induction. So go and watch the lecture video for the introduction, how to approach this kind of problem. So, but for now, what we have to do is I have this expression here that we are going to try to prove using mathematical induction. So I'm going to kind of guide you on how we approach this kind of problem, how to use mathematical induction to prove such things. So here is the general techniques on how to use mathematical induction to prove a statement. So whatever you have a problem, you can try to define your problem as an expression P of n. So if you consider, so if you let P of n be whatever you are trying to prove, so this is going to be an expression that's a function of n. So your n in this case is your variable of interest. So n is whatever you are interested on. So basically you're going to emphasize on n. Emphasize on n's means that for the base case, you consider n equal to whatever you have for the initial value. Then you assume that P of n is true. So to prove that P of n is true, so what you do is you have to consider what you call the base case. So what you do is you prove P of the n equal to the initial element. So you prove that P of n equal to the initial element is true. So here, for example, the initial element could be like if n is a set of natural numbers, if n let's say n is greater or equal to 0, you must show that P of 0 is true. So this is what we call the base case. Now, the second step is what you call the inductive hypothesis. This is what we call the inductive hypothesis. So for this, what we basically do is you assume that P of n is true. So you assume P of n is true. That's it. You assume that whatever is given, whatever expression is given here is true. So you assume that P of n is true. Now on the inductive step, you show that P of n plus 1 is true. So you must show that P of n plus 1 is true in the inductive step. So again, you can see that we have 3 steps here. You must show first the base case. You assume the inductive hypothesis. Basically, you assume whatever is given is true. And then the last step, you must show that in the inductive step, you must show that P of n plus 1 is true. So this is like the general technique. Let's just pick whatever you have here. So let's pick this particular example and try to use that technique to prove it. So I'm going to break down this problem step by step so you can see all the steps that we require for this kind of proof. So the goal is to show that for all n in set of natural numbers n greater or equal to 2, n factorial is less than n to the n. So what I'm going to do is I'm going to say that let Pn be the statement that for all n greater or equal to 2, n in the set of natural number n factorial is less than n to the n. So that's my statement that I call in this case P of n. Now for the base case, what I'm going to call A here, what I'm going to do is what's the base case? And what you can see here is that we said that n is greater or equal to 2. So for the base case, you must consider n for the base case. So for the base case, show that p of the smallest value of n, so show that p of 2 is true. So p of 2, we must show that p of 2 is true. So what is p of 2? So I call this b. What is p of 2? So p of 2 is what? So p of n, the expression was p of n was given that by a set of p of n was given by 2 to the, it was n factorial. So p of n was given by n factorial less than n to the n for n greater or equal to 2, and n is a natural number. Say n is a natural number. So for this, we say that p of 2 is going to be the expression 2 factorial less than 2 to the second. So in this case, it's not sure that true p of 2 is true yet. So now I'm going to do something else. I say that C show that p of 2 is true. So for the p of 2, we got 2 factorial less than 2 to the second. So what I'm going to do, I'm going to break this down into parts. So 2 factorial is 2 times 1, which is 2. And 2 to the second is 2 times 2, which is equal to 4. And from this, you can see clearly that 2 factorial is less than 2 to the second. So we prove that p of 2 is true. So p of 2 is true, right? So we show that p of 2 is true. Now what is next? So I'm trying to break down all the steps so you can see exactly what you need to do. So now that we show that p of 2 is true, so for the E, and I call this E, I'm going to ask you what's the inductive hypothesis. So what is the inductive hypothesis? So you can say that I said that in the inductive, what we said here is inductive hypothesis. We assume that p of n is true. So from here, you can see that what I said from the inductive hypothesis, you assume that p of n is true. So here, what we're going to say that for the inductive, what's the inductive hypothesis? That the inductive hypothesis is the assumption that p of n is true. That said, we assume for all n greater or equal to 2, n is a set of natural numbers, we have n factorial is less than n to the n. So this is what we call the inductive hypothesis. So basically we assume this to be true. Now we go next to the next expression for f, what I call f here. And I say that what is the inductive step, and what do you need to prove here. So in the inductive step is so for the inductive step, we assume P of n, and we must show P of n plus 1. So it's the same as saying that P of n imply P of n plus 1. So this is like the inductive step. So I said that we assume P of n and we must show P of n plus 1. So it's the same as saying that P of n imply P of n plus 1. So now for this question we have two questions. We have this: what's the inductive step? So for what's the inductive step, this is what we did here. The inductive step is this, and what do you need to prove? So now we must show that we need to prove that n plus 1 factorial is less than n plus 1 to the n plus 1. So that's what we need to prove. And what you can see is that we just pick this initial expression, which was what is the expression? So basically we just pick this initial expression, and we replace in this we replace n by n plus 1 everywhere there. So this is what we have to show in the need to prove for the inductive step. So we must show this expression, right? So in the inductive hypothesis, we assume that we have, because we assume that P of n is true. This implies we are saying that n factorial is less than n to the n, right? So how can I go from this expression to this? So usually you have to use your intuition here. So what I'm going to do is sometimes you can go straight from this expression and use this somewhere. I'm going to pick one example like that. But in this case, you can just go from the fact that we assume what we assume to be true. So we assume this expression to be true. I'm just going to go from there. So this is assumed to be true because of the inductive hypothesis. We are going to try to use the inductive hypothesis to show the inductive step. So from here, what I can do is I multiply both sides by n plus 1. This implies n plus 1 times n factorial is less than n plus 1 times n to the n, right? So we have n plus 1 times n factorial less than n plus 1 n to the n. So what I can do, I can transform this further. We know that n factorial is n times n minus 1 factorial. So basically this is like n plus 1 factorial, which is less than n plus 1 to the n, right? The reason is, if you say n plus 1 factorial, this is going to be n plus 1 times n plus 1 minus 1 factorial, right? This gives you n plus 1, then this is going to be n, right, factorial, which is indeed n plus 1 n factorial. So we can replace this expression by this. So that was an explanation on why I went from the first statement to the second. Now we have this expression. So another observation that we have is, if I say that n to the n is always going to be less than n plus 1 to the n, right? Because all these are integers, n is an integers and n is greater than 1, so this equality is always going to be true, right? So what I can do is, using this equality, I can go from this statement. Basically, I can go from n plus 1 factorial less than n plus 1 n to the n, which also is less than n plus 1 n plus 1 to the n, right? So this is trivial. The reason is because this expression is always going to be less than this, so that is fine. So from the, and since I have this, I can go from this expression to this. So this gives me indeed that n plus 1 factorial is less than n plus 1 times n plus 1 to the n, right? So from here we get n plus 1 factorial less than n plus 1 to the n plus 1, which is what we was trying to prove, right? So we prove our inductive step. Again, you can say that from here we use the inductive hypothesis. So we went from the inductive hypothesis, which is we assume that this was true. So if we didn't assume that this was true, we should not be able to go from this to this expression. So we are using this because we assume to be true. And you have to be careful. In some cases, you are going to still go from the inductive hypothesis to prove, and in some cases you may need to use the inductive step. So you may need to go from something like this, maybe try this way, try to go from here, then use this equality somewhere to get up to whatever you have here. So that was how to use mathematical induction to prove. So I'm going to stop here this way, and on the next video I'm going to pick another example that to again illustrate how you can tackle such problem. Thanks.